Good morning, everyone. Thanks for signing up and signing in this morning. This is the first of a five-part webinar series on nutrient optimization. Today, I'm going to be the main presenter, and then Grant Weaver with Grant Tech Solutions will be coming on shortly, but he'll be covering some of the later webinars. And then we also have Tom Stiles with us of KDHE in the early part of this webinar. All of us are working in our own fashions in the nutrient removal and nutrient optimization playbook, and we'll cover a little bit about our respective roles. We have flexibility in today's class to go back and recover something. Since I'm the main presenter, Grant Weaver may be able to better explain it than me. So we have multiple ways to answer those questions. Also, if you are on a single computer and there's multiple operators there in the room with you, please put down everybody who is at that computer so we can ensure that we get the CEUs. With that, we will begin. So this webinar series for nutrient optimization is a series of 5 webinars. This first one is right where you are today, kind of an overview. We'll be touching upon some basic optimization themes, basic nutrient removal, also kind of what to expect from a regulatory perspective over the coming years with regards to nutrients. And we will also talk about some of those questions that you might get asked by your city managers or your city councils, like, why are we even doing this? We're going to cover a little bit about the science behind nutrients and water quality issues. November 15th, we're going to talk about some case studies from here in Kansas where nutrient optimization has worked quite well. So we'll be covering those next week. Same time. Gonna skip Thanksgiving week. I know many of you will be working, but a lot will be traveling or just trying to do a bare minimum to keep the plant running on that Wednesday before Thanksgiving. So we're skipping over to November 29th. We're going to talk specifically about nitrogen removal concepts. So this will cover both the conversion of ammonia into nitrate, and then how do you get those nitrates out of the water later on in your process. December 6th, we'll be talking about phosphorus removal concepts. So kind of the same idea as the nitrogen class, just focused on phosphorus, both from a perspective of biological, and we'll also talk about chemical phosphorus removal. Phosphorus is a little different than nitrogen and is in that there are some chemical removal options out there if your plant cannot do it biologically. And then the final webinar of the series on December 13th is a review of the previous 4 webinars. So we'll go back through for many operators. When you were getting licensed, there wasn't a whole lot of information on biological nutrient removal. So we feel repetition is a good way to help gain good knowledge and understanding of the concepts here. So there are 1.5 CEUs per session of wastewater credit. You do not have to come to all of them. Each one stands independently from a CEU point of view. So that's good if you have to be out of town or can't make it or whatever. You'll still get 1.5 hours for everyone you attend. And also if you just don't really want to attend some of these, let's say you think you have nitrogen down really well, but you don't understand phosphorus quite so much, that's fine too. You'll still get credit for those that you attend. All right, so who's talking to you right now? My name is Nick Willis. I'm with the Environmental Finance Center at Wichita State University. This is a pretty big chunk of my day job. It has been both nutrient optimization work and in previous years, jar testing. Many of you have signed up. I've been to your plant for one or both of those purposes. I also have done a lot of work in asset management, rates and finance training, and then technical assistance of various types for water and wastewater utilities. Prior to that, I was the assistant utility director at Hays, Kansas. Anybody who's been in Kansas, especially Western Kansas, understands that they have some challenging water issues there, primarily with water supply. So I have a lot of budgetary experience back from that time. My first job out of college was an NPDES permit writer for the state of Arkansas. So I was a person, putting those terms and conditions and the limits and putting permits to public notice and interfacing with consulting engineers as a permit writer for the state of Arkansas. My educational background, I have biosystems engineering degree from Lincoln, Nebraska, and am a registered PE in Kansas. I'm going to let Grant talk about himself and who's this other guy who's working along with us.
All right, the other guy is Grant Weaver, another native Kansan. I think Nick grew up outside of Sterling, isn't that right, Nick? And
mostly, yeah.
And I grew up in Wichita. Yeah, like Nick, I've been in operations for a number of years. I'm licensed in a few states. Somewhere along the way, I moved out to the East Coast. I now live in Connecticut. Kind of what I've tried to do is I started this company 25 years ago called the Water Planet Company, which I'm still a minority owner of. But that company operates a number of small treatment plants here in Connecticut. And there's been a big push in Connecticut for 25 years ago, going back 25 years, for Long Island Sound for nutrient removal. So in operating these little plants, they weren't operating that well for nutrient removal. And I had to educate myself on how to get first nitrogen removal and then later phosphorus removal out of all kinds of different technologies. And along the way, it came to me that I'm not the only person struggling with this. And so then started traveling around the country. First got Montana interested, Tennessee, and then Kansas has really embraced this effort. So that's who I am. I think I'll be leading 3 of the sessions. So I'm the sandwich. I'm the inside of the sandwich. Nick's the bread. So he's doing the intro and the final one, and then I'll be leading the other 3. So, but we're both around, and I've accompanied Nick on, I don't know, 50 probably treatment plant visits out of the almost 80 I've made there in Kansas. So I'm his worse half, I guess, and Nick's my definitely better half in this whole arrangement. With that, I'll clam up and give it back to you, Nick. This is your show.
Okay, now we're going to turn it over to Tom Stiles with KDHE for a little bit of their perspective as the NPDES permit issuer for the state of Kansas. So, Tom, if you're there.
Yeah, if in this information sandwich, if Nick and is the bread and Grant is the main meat, I'm just the condiment here. But I want to kind of just give the perspective from KDHE. We wholly sanction efforts to try to do optimization. Nutrient reduction has been a priority for us for well over 20 to 25 years. We have certainly pushed our mechanical plants to start looking at reduction since 2004. Early on efforts of that basically were capital investments for biological nutrient removal. And we had a number of plants adopt that technology. One thing we've noticed is that once the operators had the new technology in hand, they became quite proficient at making it at work. And in front of you is kind of a classic example of this down at El Dorado, where they've installed BNR, but their operators have routinely been able to produce effluent that is low in nitrogen, but in our targeted nutrient, phosphorus, where we set a goal of 1 milligram per liter. They've been operating consistently at or below that enhanced nutrient reduction level of 0.5 milligrams per liter. That translates, and that's the goal is not regulatory. It's just basically an operational objective there. The regulatory limit is a mass-based limit of for phosphorus that basically just combines the concentration output with the effluent volume that's discharged. And El Dorado, because of its good performance, has consistently remained below its waste load limit of 25 pounds per day with its phosphorus there. As we began to see this type of example where capital investment was made, but then we had operator proficiency build up, we became more and more enamored with optimization as a means to really take hold and help systems drive down their nutrient output. Later on in these presentations, Nick and Grant will talk about kind of the polar opposite, the other end of the spectrum with the city of Great Bend, that with some small investments in instrumentation and mechanical equipment has been able to drive down its output of nutrients from its oxidation ditch system without the need for investing in BNR technology. So it basically represents the high watermark when it comes to the ability of optimization to meet nutrient goals there at a fraction of the cost. We also know that with things like phosphorus, that chemical feeds are very efficient at knocking down, whether it's alum or ferric. But it comes at a cost, and it comes with complications in building up your sludge and biosolid management. Optimization creates the opportunity for biology to do the heavy lifting, to take out the nitrogen and phosphorus without the commensurate amount of sludge being potentially produced there. My advice, as I said, we sanction optimization, and in doing so, we encourage systems to do adaptive management, try things. We recognize some things won't work. There's failure. Sometimes that as a consequence of maybe a burst of elevated ammonia as a result of some process change that you're trying to take. We accept that as a viable and valid reason why there was a potential violation of a permit limit in the course of trying to work on the big picture of nutrient reduction. And we will work to minimize your regulatory risk in trying out some of this experimentation. My advice is that embrace the services that Nick and Grant provide, and bring them on site and have them understand what your world is like. This is not a book learning exercise. It's not something you can just read up on and then go out and put it into practice. Practice and real world experience is the only way that you'll become very proficient at this type of operation. Trial and error is just inherent in that process. There are two big needs if you're going to pursue optimization. One is operational data, and the other is human operational experience, to understand what the data are telling you and how to basically work the system to respond to what the in-house data are indicating and what the prevailing conditions are within the treatment train. The question of why go this route rather than maybe what I think optimization does is a good first step. It helps you build some street cred to basically say, hey, we've tried some cost-effective means of doing it. It doesn't work for everybody. But before you necessarily jump into large scale capital investment in putting in new treatment technology like BNR or ENR, trying to work with what you have with some tweaking and some additional instrumentation and some alteration in the way you process wastewater through your system is a good first step toward saying, can we get by just with what we have, or ultimately are we looking at beginning to make a major upgrade? And again, it's not for everybody. It depends on your system. Activated sludge, oxidation ditches, sequential batch reactors are all primed for opportunities for optimization. If you're running a plant that's a trickling filter or a rotating biological contactor, that's pretty antiquated treatment technology that is just screaming for need for upgrade in and of itself, and optimization is not the path to do that. So for those of you that have some of those systems that have got some inherent flexibility and ability to be manipulated, this optimization approach is something worth pursuing. And carry on those conversations with us. Utilize the services of Nick and Grant to try things out, and we can help to each other work toward achieving the state's nutrient reduction goals. Nick?
All right, thank you, Tom. And I will also note that the person I work most closely with at KDHE is Ryan Eldridge, most of my conversations with you all are copied to him, so he is always in the loop with respect to any operational or processing changes that you're trying at your facility. And then that goes right back to Tom. If there's a high ammonia, then KDHE knows what is going on and the reason for it. So definitely a learning by doing, as Tom has discussed, and as we noted, we will be covering some of the case studies that from a financial point of view for your utility ratepayers, and the ability of your utility to keep up with things that aren't your treatment plant. Optimization, if successful, can really bear some big dividends for the sustainability of your wastewater utility as a whole. So your collection system and the ability to staff your plant and to afford the things you need going forward. With that, we're going to talk a little bit now about why nutrients are even a thing. So what are the issues with nutrients? Fundamentally, it really comes down to ecosystem productivity of the receiving water bodies. So bear with me for a second. So your rivers and streams are ecosystems. There's primary producers, which are mainly things like algae, and then there's higher level organisms that feed on the photosynthetic, primarily organisms in an ecosystem. So in Kansas, we have some forest in the southeast, and then our native ecosystems are primarily grassland, and when it comes to dry lands. And every ecosystem will tend to have one or more factors that limit the productivity of the ecosystem. So the primary productivity is basically the plant growth, or in the case of water bodies, primarily the photosynthetic organisms dominated by algae and cyanobacteria and other photosynthetic organisms. And for some examples, for deserts, generally the limiting factor for plant growth in deserts, and thus the number of animals that can eat the plants and the number of predators that can eat the animals that eat the plants, is going to be water. There's just not enough water in deserts to have a lot of productivity there. For cornfields, those of you who've been around farming, typically it's going to be nitrogen, phosphorus, or water. And it can vary depending on the year. So many times, if like this year, many fields would have had sufficient nitrogen and phosphorus to grow good corn yields, but it was a drought, and dryland agriculture didn't have enough water to produce what the farmers had hoped for. Soybeans are a little different. they produce their own nitrogen with symbiotic bacteria. And soybeans are typically going to be limited by something like the pH of the soil. Legumes don't like acidity. And then phosphorus can also limit it, or just like corn, if they're in deserts, if there's not enough water, they won't grow that well. An ecosystem like tundra, in the wintertime, that's going to be very restricted by sunlight. It's cold enough that the plants get covered by snow, and then also, depending on how far north you go, the amount of hours of sun in the day are limited, and then temperature as well limits productivity there. Freshwater ecosystems, getting more to what today is about. Generally, the limiting nutrient for additional growth of photosynthesizers in the water column is going to be phosphorus. And we see this at lakes and reservoirs, ponds in Kansas, that we are seeing increasing phosphorus levels and increasing amounts of algal blooms in these freshwater ecosystems. You have some of the same dynamic occurring in rivers. It's just that you kind of have the flow that keeps the harmful algal blooms that we see in lakes from occurring there. In saltwater, unlike freshwater, typically the limiting nutrient is going to be nitrogen. And we'll talk about that in the next few slides. Now, what about the ecosystems you run as operators on a day-to-day basis? So in a typical activated sludge treatment plant, there's probably 3 primary limitations to what is going on there. So in activated sludge, you need that aerobic environment for your ammonia conversion. If you do not have enough dissolved oxygen, that is going to be limiting the productivity of that system, the ability of it to do what it is designed to do. Now, if you're trying to remove that ammonia again, the pH can be limiting. Likewise, temperature. If it's too acidic, there's not enough alkalinity in the water, your nitrifiers don't work well. Additionally, time can be a limit in an activated sludge treatment plant. The organisms take time to perform their conversions, and if the water isn't in there long enough, you won't get what you desire. Moving on to these nutrients within freshwater ecosystems. Now, at your plant, you have incoming ammonia. Almost all of the nitrogen at most plants here in Kansas is coming in the form of ammonia. That ammonia is toxic to organisms, so converting it to nitrates, and if this is going over your head, that's fine. We'll be talking about that later in this webinar series. So you convert ammonia, which is toxic to nearby organisms near the outfall of your plants. You convert it to nitrates. Nitrates are typically not toxic at the amounts you would see to freshwater organisms. So that's good for the freshwater organisms. However, all of that nitrogen is still basically in the water. It's just in a different form from ammonia turned into nitrates. Nitrates are problematic themselves, but they're problematic in different ways than ammonia. So first, especially in Kansas, where we have a lot of systems with limited water supply options for drinking water supply, the Safe Drinking Water Act has a maximum contaminant level for nitrates. So if you're upstream of a drinking water intake, making sure you control nitrates is helpful to your neighboring communities. It's especially so during times of low flow, where your discharge from your wastewater treatment plant ends up being a large portion of the receiving water body flow. And there's quite a few systems that are like this within Kansas, where systems downstream are pulling from a river that, there's a wastewater plant 15 miles upstream. So nitrates are going to be an issue there in your immediate vicinity. Now, further from your plants, nitrates will lead to brackish. So that's kind of in between ocean water and fresh water, so saltier types of water, and saltwater eutrophication. So eutrophication is very, very high primary productivity, large amounts of algae blooms going on. Nitrates are problematic because of the Gulf of Mexico dead zone. So this is from 2021. There's basically an area of water kind of at the Gulf of the Mississippi River, spreading on the south side of Louisiana over to Texas, where there's very, very little dissolved oxygen in that water. So it's a dead zone because the species that would live there, fish, crabs, shrimp, things like that, are unable to, because there's not enough oxygen for them to survive. So the red here is the deadest of the dead zone area. So less than 1 milligram per liter dissolved oxygen. Here's a graphic of kind of what is going on in the dead zone. You have this plankton or algae growth occurring, and it's occurring in such a high rate that it doesn't have nothing is able to consume it higher up the food chain. So it just dies. And when it dies, it sinks to the bottom, and then you get decomposition, which consumes oxygen, and it leads to very low oxygen levels in that dead zone. So if you are a species that can move quickly, such as large fish, and there's suitable habitat nearby, you're going to leave. If you're a species that can't move very quickly, such as a crab, or fish that can't survive in deeper water, you end up, there's a pretty high likelihood that species is going to die in that localized area. So this is a basic idea of the issue of nitrates in kind of the Midwest Mississippi River watershed. It's a very large problem. Your plant is a very, very, very minor contributor to it, but it is a contributor. And so are every single farm field within the Mississippi River Basin, and everybody has to do some level of reduction of nitrogen discharges in order to help remedy this Gulf of Mexico dead zone. This is an area where people have their livelihoods, tourism and fishing industries, and it's impactful to the economy, both locally down there and nationally through things like seafood production. So this is the reason that nitrogen is an issue. Locally Safe Drinking Water Act, more broadly, it causes problems in the dead zone in the Gulf of Mexico. I'm going to switch to total phosphorus. What's going on with total phosphorus? It's really not that much different than what's going on in the Gulf of Mexico. It's just that it's more localized to your nearby water bodies, in that excessive phosphorus increases freshwater biomass production. Very, very similar to that dead zone in Gulf of Mexico, you increase that algae production. I believe this is Milford. The water is green. Water is not supposed to be green. And this is a very hyper-eutrophic lake where the biomass production is basically about as high as it can be, given physical limitations. Excessive algae is a problem. It can be toxic where harmful algal blooms are in place. The KDHE runs a harmful algal bloom program, and even to just a few weeks ago, there were still lates in harmful algal bloom warnings. I haven't checked recently. I think with the cooler weather, it should be dropping. This algae up top also can shade out some of the lower parts of the lake where there might be attached growth plants. If you're a drinking water provider pulling from a lake with algae blooms, not necessarily even harmful algal blooms, there can be some kind of nasty taste and odor issues associated with it. Many lakes on almost an annual basis, we'll have recreational areas closed due to harmful algal blooms. If you're running a treatment water, a drinking water treatment plant, algae can severely complicate your day-to-day operations. Additional chemical is often needed, and how you operate your plant may have to change. You can also see fish kills in some cases with this. Likewise, there's always a few animals that get sick or die due to exposure to harmful algal bloom toxins. Where is phosphorus coming from? In your wastewater treatment plant, it's predominantly coming from people. So if anybody has a bottle of soda, turn to the ingredient list, you will see some sort of phosphate. Those are added for kind of a food preservative perspective. Your body does not need that phosphorus in any sense or form. We do need some to live, and it's almost never a restricted nutrient in anybody's diet. So we're through food preservatives, we're eating far more phosphorus, many of us, than we need to have, and that is being excreted primarily in urine. So we're the source of most of the phosphorus at most wastewater treatment plants. Not always the case, though. Historically, there's been a lot of phosphorus in detergents. Those have been more or less eliminated from the market for, kind of home domestic consumption. It's a very minor contributor at this point. Fertilizers can also be a source of phosphorus. For your wastewater treatment plants, flows is probably pretty negligible, although you may have some spikes now and then from somebody cleaning out a fertilizer tote or something like that, or if you have fertilizer production in your community. To the watershed as a whole, animal waste can be a pretty high contributor of phosphorus. So depending where you are and what level of animal production there is, that can be a pretty big source of phosphorus. There are industrial sources of phosphorus that you need to be aware of. So food and beverage processing, in my experience at plants here in Kansas and elsewhere, communities that have significant food and beverage processing often have much higher incoming phosphorus levels. And this is related to that food preservative for one case. So as they're cleaning off, waste that's attached to production processing equipment, some of that preservative will end up in the wastewater treatment plant stream. Additionally, industrial sources will use cleaning products that contain phosphorus sometimes. So this, if you are struggling and you know that you have food production in your community, having a dialogue with some of the producers to see if they are using cleaning products that contain significant amounts of phosphorus, that might be your most cost-effective way to reduce phosphorus at your plant. That doesn't mean optimization is something that's off the table. It's just that minimizing from the get-go can be pretty useful there. If you do have fertilizer production, again, that can be a source. And then one thing I see very commonly is metal finishing operations. And this is generally done in the cleaning process, phosphoric acid and similar compounds. And oftentimes in the metal finishing, metalworks industries, the loadings are inconsistent due to the production process, that they might clean a batch of product on a single day and then have very little discharge on further days. Food and beverage processing is going to be more consistent in most places. So I'm working with a few communities that have metal finishing operations, and we're trying to get our heads around, what is the actual amount of phosphorus, how consistent is it coming to us, and if you do suspect industrial sources, feel free to reach out to me. I think that smaller communities with industrial sources certainly may need to have more data to understand what's going on than your monthly grab samples that many facilities have. A monthly grab sample could be representative, or it could be very, very, very far from what is your typical phosphorus level, especially if there's some sort of a batch discharge going on. That's when you catch it. I've seen influent phosphorus levels of 60 to 90 milligrams per liter. I don't think that's typical, but that is the information that the plant has. So oftentimes more data is going to be needed if you're suspecting high loadings from industrial discharges. We're going to move on to kind of the nutrient regulation within the state of Kansas. What is it looking like for facilities, and what are some of the expectations as permits get renewed? I'm going to throw a big caveat on this in that nobody's perfect at predicting the future. There can be other regulatory drivers. I was just at a Missouri Water Environment Federation conference that said there might be increasingly stringent limits on facilities that discharge into tribal lands. So if you're above Oklahoma, that could change this trajectory. We really don't know. It was one of the kind of regulatory updates there in Missouri. So big caveat, this is what probably is most likely to be expected, but it does not mean this is what you will actually see. So within Kansas, most wastewater treatment facilities that are mechanical can expect some of the following. So as Tom alluded to, mass-based limits are the expectation for most facilities. Now, the most likely facilities that would have a concentration-based limit may be related to nitrates because of the MCL and Safe Drinking Water Act. So keep that in mind if you're above a surface water intake, particularly if you're pretty close to them. But for mass-based limits, the mass that your facility is going to be facing on a daily pounds per day calculation is going to be 10 milligrams per liter, and then for total nitrogen, and then 1 milligram per liter for total phosphorus. These are typically going to be implemented as a rolling annual average. So rolling annual average is the last 12 months, and it moves every month forward 1 month. So keep in mind that some facilities may be getting hard limits for total nitrogen or for nitrates related to drinking water MCL. And there also may be some watersheds where a more stringent phosphorus limit driven by TMDLs is going to be necessary to protect water quality. I think if you're a facility in one of these watersheds, you're probably aware of that at this point. What does this mean to you as a facility? So with a mass-based limit, you almost certainly can discharge higher than a concentration-based limit. So let's say we have 10 milligrams per liter as a concentration that was used to derive our mass-based limit. So if you have a plant designed at 1 milligrams per liter, or 1 million gallon per day, and you're putting out 500,000 gallons per day, the concentration can essentially double and you'll be in mass-based compliance. So you could put out total nitrogen of 20 milligrams per liter, assuming you didn't have a limit related to nitrate or a drinking water MCL, and be in compliance with that mass-based limit. So this goes back to kind of, operator level 1 math, where you calculate the mass from a concentration. It's your flow rate in MGD times 8.34 times the concentration. So that'll give you that mass-based limit. So obviously, if you reduce one of those numbers by half, you can double another and get the same value. What does a rolling average mean? A rolling average means that in some months, it's perfectly fine to exceed a mass-based limit as long as that is equally offset in subsequent months. This is both beneficial and can be problematic to you. So it's beneficial to you if you're operating, close to that mass base limit. Some months you're 20% under, some months you're 10% higher. That gives you flexibility in how you operate, and you can have little hiccups here and there, and you can still be in compliance. That being said, one bad month can cause months of non-compliance. So if you have, you're typically putting out phosphorus of 1 milligram per liter, bouncing around, doing really well, and you're close to your design flow, you're really good until that month where, for whatever reason, you put out phosphorus of 7, 5, whatever, milligrams per liter. That is going to stick with you for the next year. And it's really hard to balance out a very, very high value. And this is going to be particularly problematic for most plants with phosphorus over the next 12 months. So if you have limited sampling frequency for your DMR reporting, and you have a mass-based limit, so let's say you're a facility that has a mass-based limit for phosphorus, and you only sample once a month on a required basis, you might want to consider how you sample and when you sample. So I would typically encourage you to sample very early in the reporting window, such that you get your values back. So if you get a value back and it's 0.8 milligrams per liter total phosphorus, don't sample again. But if you get a high value back, say 3, 4, 5 milligrams per liter total phosphorus, you want to pull another sample, because hopefully that hiccup didn't last the entire month, and you will be able to bring your monthly average that goes into that that annual rolling average down some. So if your first sample was 4 and your second sample was 1, then your monthly average that goes into that 12-month rolling average ends up being 2.5 milligrams per liter instead of 4 milligrams per liter. And how the math plays out on that is very beneficial to you if you can bring any high values down. So very, very important to understand the dynamics of sampling, frequency, and how it impacts that rolling average if you are under a rolling average. And if you're questioning, like, I don't really understand what he's saying, feel free to reach out to me. But also, you can calculate that monthly rolling average in your own facility, and you are very likely to see that one single month could have caused multiple months of problems of compliance there. All right. So hopefully you have a good understanding of the issue of nutrients, how the state of Kansas is approaching nutrient optimization. Now we're going to move into, like, why nutrient optimization? Why don't we just build a new plant? And I've been to enough facilities that I've met many operators who would love to have a new plant. And that might be because, things are obsolete, things are falling apart. And I get that. KDHE wants you to continuously reinvest so that, your plant works well and that it's a safe place to operate. But when we look at the broader scope of wastewater utilities, nutrient optimization will play a key role, primarily because of the sustainability it brings about to your utility from a financial point of view. So, as you're all aware, wastewater systems are facing numerous pressures. I have been to very few communities that don't have significant collection system investment needs, whether this is you have very high inflow and infiltration, or you have lift stations that are periodically flooding, or lift stations that are just kind of at the end of their life. Very few systems in Kansas don't have significant collection system investment needs. There's only so much money you can extract from your ratepayers to keep your utility going. So if you have a gold-plated wastewater treatment facility, but your collection system is falling apart, That is not ideal. So nutrient optimization, if successful, can help balance the needs of treatment and collection at your facilities. Aging infrastructure in general, this extends to other utilities that your community may operate. And there's not a single city commission in the state who doesn't look at both water and sewer bills. So if your community is having to significantly invest in water treatment, water distribution, that can limit the ability to charge for more projects on the sewer side. So even though you may be in separate departments, from a political point of view, from a financial capacity of your customers, aging infrastructure of water or electric or natural gas utilities will impact what you're able to do as a wastewater system. We've also seen equipment supply chains. I think a lot of utilities are ending up having more inventory of spare parts than they used to run with. That comes at a real cost. You may also see more expensive replacements of some of the equipment necessary to operate your collection and treatment systems. These have maybe gotten a little bit better, but it's unlikely that the additional costs are going to come down a whole lot. Then we have a lot of kind of like, I don't know what's going to happen here. Emerging contaminants. Primarily, the focus right now seems to be on PFAS and PFOS. Those are in your wastewater treatment plant biosolids right now. And there's one state in the country that has banned land application, which is Maine. And I spent a week earlier this year in New Hampshire, and believe me, that got everybody's attention there. Maine facilities anecdotally are reporting about 3 times higher cost for biosolids as a result of a ban on land application, because they're trucking it to out-of-state landfills at this point. We don't know what PFAS regulations will be on biosolids, but there's reasonable chance that what you're doing today with biosolids may have to change in the future because of PFAS, PFOS, possibly because of some other emerging contaminants that are out there. It's high on a lot of regulators' radar. Hard to say exactly where it's going, but there is it's within reason to expect that some of the standards for biosolids may change in the future. Additionally, some facilities may have PFAS on their discharge, which is a whole other can of worms to open. So I guess what I'm saying with this is, run a tight ship if you can, so that you're able to deal with things that may come into the future. I'm not trying to scare you, but there are things on the horizon that could be quite pricey and difficult to deal with. There's also communities, particularly a problem in the Great Plains, that have stagnant or declining populations. So this plays into long-term utility sustainability as well. Stagnant and declining populations means that there's not additional money typically coming into your community to pay for infrastructure. So you have to be that much more careful when you come to looking at how things are handled. Every single one of these can pressure utility finances. So how does nutrient optimization benefit utility finances? So particularly in the nitrogen webinar coming up later, you'll see a reduction in energy usage with the use of anoxic zones for denitrification. And if you don't understand it, no problem, you will after we cover it. If you are using chemicals, either for pH adjustment or for phosphorus removal, you can see reduction or possibly elimination of chemical usage. So this is alum or ferric for phosphorus, alkalinity addition for denitrification, which is going to be pretty rare in Kansas. There are a few facilities that have some sort of caustic addition, though. Additionally, and Great Bend's case study, which we'll get into in a future webinar, elimination or the delay of need for capital investment is really, really strong here. And you'll see good examples of this. Your facility may vary depending on what you can get away with as far as minimizing capital investment need. But there's a lot of facilities that with minimal capital investment are going to be able to meet mass-based limits at some point in the future. And then again, your treatment plant is only part of your wastewater system. If you have a certain pot of money to spend and it's all spent on wastewater for compliance with nutrients, that is likely going to starve your collection system of resources. So trying to balance the needs and the resources devoted to both of those is important. So the theory of nutrient optimization at a very high level is that you guys can operate your plants differently than plant design, and many of you already do. Nutrient removal is really all about having the right environments in the right places at the right times. So those of you who have a biological nutrient removal plants are largely doing this by design. The flow has been designed from day one to be in the right place with the right environment at the right times. Other plants are going to rely more heavily on operator skill. Not that facilities that have B&R don't have skilled operators. It's just that those who are doing nutrient optimization have to be a little more comfortable stepping a little further out on that limb and seeing what works. At a high level, your environments for nitrogen removal in most plants are going to be a two-step process. And we will get into much more depth of this later on in the presentations. You need an aerobic environment where ammonia is being converted to nitrates. That's typically about 6 hours of time is necessary for that water to be there. That is necessary for that conversion of ammonia to nitrates. Then you need some anoxic time, which is very, very low dissolved oxygen, where that nitrate is converted to nitrogen gas. You need about 2 hours, 1 to 2 hours for this conversion to occur. And you need to have some sort of carbon source. For most plants at the limits we're looking at in Kansas, you'll have sufficient incoming BOD in your influent to do this. Though for really low total nitrogen levels, or if you have very low influent BOD, you may need to add carbon to achieve this. The environments for phosphorus removal are different than for nitrate removal. I will note, however, if you are unable to drive nitrate levels down, your chance of having success at biological phosphorus removal is quite low. So what you need for phosphorus removal, you need to have a location where volatile fatty acids are produced. For most facilities, this is an anaerobic zone with sufficient carbon. So an anaerobic zone means zero oxygen is in the area. Most facilities, this is going to be your influent and your return activated sludge. So your influent has the carbon, your return activated sludge has the biology. Now your bio-P organisms, those that take up excessive levels of phosphorus from, dissolved phosphorus from the water, consume that VFA. So it's sort of like you and I, going to Golden Corral and eating too much, we get fat, and then we can use that energy over the coming days, and hopefully we all do. These bio-P buds consume that VFA in an anaerobic zone with carbon, so it's typically the same tank as fermentation occurring. In this process, where they're consuming the VFA, they'll actually release phosphorus back into solution. So, this step is to remove phosphorus, you need to add more phosphorus from your biology. So it doesn't make a lot of logical sense, but if biological phosphorus removal is working at your facility, the water going in to your fermentation area, your anaerobic zone where VFA is being consumed, should be about the water out should be about 3 times higher in phosphorus than what is coming in. And that is an indicator that things are going well in your anaerobic zone. Now, your phosphorus uptake occurs in an aerobic environment. So this is the same place where your ammonia is being converted to nitrates. So in biological phosphorus and biological nutrient removal facilities, there's a lot of kind of different layouts of the flows and which tank goes first versus second. Here's a high-level diagram of what is going on. So generally, most plants will have something like the top level where you have influent and RAS going into an anaerobic zone, that you have the fermentation, VFA production, VFA uptake there. It will then pass into an anoxic zone. In that anoxic zone, you're getting recycle from the end of the aerobic zone. This is high in nitrates, and the anoxic zone should hopefully have enough incoming BOD that's passed through the anaerobic zone, hasn't been consumed there, to denitrify in that anoxic zone. Then it's directed into the aerobic zone. You get that ammonia conversion, and you also get luxury phosphorus uptake. Your nitrates, the nitrogen is ultimately being removed from your plant in your anoxic zone, where it's converted to nitrogen gas. Your incoming phosphorus is being converted into biology, and the biology is being removed with your waste activated sludge in a facility like this. Phosphorus is typically more tricky to get right, and then you can also have upsets down the line which lead to re-release of phosphorus. So once you get it in the biology, you need to keep it there as you further process those biosolids and store them in your facility. So optimization versus design. Many of you won't have a plant that looks like one of these two layouts. Your plant optimized for nutrient removal will not look like the plant, on the top or bottom here at the right. That is okay. There's many, many plants that are doing this well without having this specific type of layout. You need the environments, not the tanks. So when you're thinking about your own facility, how can your facility get the environments that are necessary for biological nutrient removal? The tankage isn't really that important. You need the right environments, right place, right time. Biological nutrient removal designed from the outset to do that. For your own facility, operator creativity can go a long ways to getting these right environments at the right times. All right, going to go back to total nitrogen here. For total nitrogen removal, again, keep in mind it's a two-step process where step one, you're converting ammonia to nitrates. So you have dissolved ammonia, it turns into dissolved nitrates. Step two, you convert nitrates, which are dissolved in the water, to nitrogen gas. Once it's converted to nitrogen gas, it goes back into the atmosphere, not your problem anymore. So we've already discussed that ammonia is toxic to life. Nitrifiers are the bacteria that convert ammonia to nitrates within your wastewater treatment facilities. They live in an aerobic or oxygen-rich environment. They are both pH and temperature sensitive. Thanks to Grant, we have a nice illustration here of what is going on in an aerobic environment with ammonia. So you add your oxygen, that consumes some alkalinity, which releases hydrogen ions. That makes your water more acidic. Here you get an intermediate step of nitrite, add a little more oxygen, and you get a pretty stable molecule of nitrate. It's fully oxidized at that point. So you have this nitrate, problematic again in the Gulf of Mexico. We know that can be problematic. To have. You need low or very low or no dissolved oxygen to occur. And I'm getting something that my connection is unstable. I'm going to turn off my video here. You also need a carbon source, which is typically going to be that influent BOD. So again, some plants need to add from time to time. When you convert that nitrate to nitrogen gas, half of the lost alkalinity is recovered, which can be very beneficial to operational sustainability at a facility. So again, what we're looking at here on the top diagram is your aerobic basin here is where the ammonia is converted to nitrate. Some of that nitrate gets recycled back to the anoxic zone, where that nitrate is converted to N2 gas. So it's that kind of internal recirculation is really where the nitrate is being removed, the bulk of it in this facility. So the benefits of nitrate removal are improved water quality, both for the Gulf of Mexico and for drinking water quality. And then you have improvements related to energy savings. And in the nitrogen webinar, we'll talk about air cycling. Many facilities, their very first step for nutrient optimization is to cycle air in their aerobic basin. Some facilities also turn off part of the aeration basin, but basically the amount of horsepower needed to supply air for your plant can be decreased, which can result in pretty significant energy savings at many wastewater treatment plants. As plants get comfortable with nutrient optimization, they often and to have good reliable nutrient optimization, they will need to control their dissolved oxygen with a DO feedback to control the speed of their blowers or their rotors that are supplying air to their system. We're going to move to total phosphorus. Again, this is a high level. There are 90-minute webinars coming up in the next few weeks that will cover this in more depth. So for phosphorus removal, your first step is the production of volatile fatty acids. So the ingredients you need here are mixed liquor solids, so your return activated sludge, and they need to be low in nitrates. You need influent rich in carbon, and you need time, maybe 1 to 2 hours. What you do in the production of volatile fatty acids is you allow fermentation to occur. So you need minimal mixing and no or minimal air introduction. And this is a key diagnostic point for biological phosphorus removal is you need to keep the nitrates and air out of your anaerobic zones. Oxidation reduction potential is also key here. If you have the ability to measure it, -100 to about -250 millivolts is the range in which you will see volatile fatty acids produced. The BioP uptake VFA, typically in the same basin as where it's being produced. It's very important to minimize the amount of nitrates that are entering this basin because denitrifying bacteria, faster growing, they will consume the volatile fatty acids needed for your BioP buds to grow well and thrive preferentially. So you can produce the VFA, but if it doesn't get to the right organisms, you won't have biological phosphorus removal occur. So the key here is making sure that your RAS is not high in nitrates. If your RAS is high in nitrates, you may have, fair to middling biological phosphorus removal occur because denitrifiers are going to consume some of the VFA instead of the organisms that consume phosphorus in your anaerobic zone. So to check your work to see if this is working well, the phosphate levels should be about 3 times the influent leaving the basin as the influent entering the basin. So 3x increase. Some facilities run quite a bit higher than that and are still able to remove phosphorus. And this oxidation reduction potential, again, in that same -100 to -250 millivolts. Third step here is, directing that fluid that is rich in the BioP buds that are fat with VFA into the aerobic basin. You will have luxury phosphorus uptake occur here in the aerobic basin. Once that phosphorus has been consumed into the biology, it needs to be removed, and that is done in the solids. So with the clarifiers in most facilities. It's very important to keep in mind that you can lose phosphorus later on. So you may remove it well in your liquid process and then see it lost in the solids processing of your facility. And we can very much help you in diagnosing what is going on with the flows of phosphorus at your facilities. So going back to this diagram, the keys to phosphorus removal are primarily in that anaerobic zone, and protecting that anaerobic zone from nitrates is very important. Additionally, it needs to be protected from high amounts of dissolved oxygen, which may be coming in your return activated sludge, or at some facilities, so if you have aerated grit removal, for example, you may be hindering your anaerobic zone creation by adding air early on in your headworks processes. So ensuring that the return activated sludge is low in nitrates and dissolved oxygen, and that your pre-processing of your influent also doesn't add too much oxygen will help in your phosphorus removal. If you are removing ammonia well in your aerobic zone, if you get step 1 and step 2 right, you will almost certainly have good luxury phosphorus uptake going on in your aerobic zone. So that is often not a limiting factor at most facilities. Common failure points for phosphorus. The first one is going to be nitrates entering that anaerobic zone. If you don't have low nitrates in your facility, you're unlikely to have good phosphorus removal because the volatile fatty acids, even if you're producing them, will be consumed by denitrifying bacteria. Additionally, high dissolved oxygen in your anaerobic zone, making that anaerobic zone really in quotes here. So you can get return activated sludge. I have seen facilities with relatively poor partitioning between basins have backflows from their aerobic zone into their anaerobic zone. And then probably most commonly, I see overmixing of the anaerobic zone, making it more an anoxic zone by entraining some of the air from the atmosphere through overmixing. We can also see release from sludge occur. So facilities will do really well in removing phosphorus into their solids, and then it's released later on in the process. Most commonly, this is going to be from deep clarifier blankets. So if you have clarifier blankets that are anything more than maybe 1 or 2 feet at most facilities, you can have anaerobic septic conditions occur where phosphorus release will happen. And then sludge processing. Some facilities will have very high levels of phosphorus that have been removed in their biosolids be released in sludge processing. I'll move on to an example here of my trip to New Hampshire. This is the town of Sunapee, New Hampshire. They have oxidation ditches. They're actually designed to operate in parallel or serially. They were operating them in parallel when I was there. Their basic operational idea is to have aerobic and anaerobic zones to remove the nitrates within the ditches themselves. So they're cycling their rotors on and off and controlling dissolved oxygen when the rotors are on. So this is the type of total nitrogen optimization very commonly done in Kansas. For total phosphorus, they have 2 parallel anaerobic basins. And let me see if I can get my laser pointer here. So these are 2 anaerobic basins, and they operate in parallel. And then the sludge processing is here under roof. So they have some New Hampshire gets some pretty extreme precipitation rates where they feel they are getting biology being washed out from the anaerobic zones. biological phosphorus removal organisms grow pretty slowly. So protecting them and their environment is important. So they're looking at some headworks changes to bypass high flows directly to the ditches instead of having all influent going through the anaerobic zones during high INI events. Some of it would continue to go through, and the balance would go straight to the ditch. And then they also fear that they are overmixed in their system. So I'll kind of show you a picture here. Here's their two anaerobic zones. Those are pretty decent horsepower motors, very deep basins. So they have to prevent them from operating as a clarifier, making sure that the biology keeps moving. They're looking at drives and also just on-off cycling of those mixers. They have found through ORP measurements that it's not deep enough. So to have a more anaerobic zone occur, if you can control your mixing, that's often a way to handle it. They've also done some unique things in solids handling, which is why I bring it up here, because it's not just optimizing the biology of your plant, it's optimizing the entire operation. So the solids handling at Sunapee, they did some jar testing after finding that the return flows from their belt filter press were really high in phosphorus. So they are dosing polyaluminum chloride, which binds orthophosphate with the polymer before the belt press. And this is an attempt to keep the phosphorus that they've removed earlier in their plant from returning to their plant. So this helps to prevent, to lessen the loading on the plant as a whole. And then they have adaptive operations. And I think most of you on the line are going to need to have some sort of adaptive operations in your own facilities. Some of the things Sunapee is doing is that they're regularly testing the phosphate leaving the ditches. They also have begun monitoring the anaerobic basin oxidation reduction potential values. So where my laser pointer is here, they're making sure it is the right environment in the first place to grow the VFAs, to have the VFAs consumed so that the ditches back here, you have luxury phosphorus uptake occur. So they're monitoring if that luxury phosphorus uptake is occurring within the ditches themselves, and they're monitoring the environments where the BioP processes are taking place. So if everything's working right, you're going to operate on a plan A here. And Sunapee's plan A is to have these anaerobic zones work well. And during the solids processing, add the polyaluminum chloride to keep that phosphorus they've removed and from returning back to their plant. Now, plan B is that they're testing the phosphate leaving the ditches here. They're going to add chemical before the clarifiers if that phosphate is high, and then they're going to use PAC during solids processing. So this is their belt, plan A. Plan B is their suspenders. So they're using chemical in a very strategic way that helps minimize the cost and downstream impacts into their facility. So they don't dose chemical all the time before their clarifiers, only when it's strictly necessary. And if Place Center is on the line, they're doing something very similar with testing before the clarifiers. They add chemical if necessary, but if things are going well, they turn that chemical off and rely on their biological process to remove phosphorus. Kind of quickly highlight Great Bend. We'll be covering it in much more depth. There's a good write-up in Treatment Plant Operator magazine. Feel free to Google it. Just wanted to show you a few graphs of their results. So they were bouncing around 2.5 milligrams per liter total phosphorus. And they worked with Grant, listened to Grant, did some of their own investigation and processing work, and their total phosphorus has dropped from 2.5, which is not bad, to under 1 milligram per liter as a rolling 12-month average. I'd like to highlight on this graph the rolling 12-month average versus, so that this is the black. You'll see it takes a while for the rolling 12-month average to come down, even though the monthly averages have gotten pretty low. So your high values do stick around with you, but towards the right of this graph, you'll see some of the benefit of the rolling 12-month average. They had a pretty high month here, but it didn't impact the rolling 12-month average all that much, and they were able to keep it flat afterwards through better performance. So this is another key to operating your facility, is understanding the impact of the rolling 12-month average. Now, Great Bend, their total phosphorus, they were right at kind of their monthly average, the mass-based limit expectation before optimization, and now they're well under it. So they were looking at, well, we might need to make investment. They did nutrient optimization. They no longer need to make capital investment to meet total phosphorus goals and ultimately limits as they roll out. Total nitrogen is a similar story, although due to facility size, they're operating well under design flow. They were already within total nitrogen mass-based goals and future limits at the facility, but they've significantly improved on their total nitrogen flows as well. Here's a little bit at the high level of what they did. They have a plant. The North Basin was offline due to low flows. They basically had a total nitrogen removal plant where they had an anoxic zone here on the left, and then they removed ammonia in an anoxic zone here on the right. There's several of this plant style in Kansas, and they all have a recycle date to have mixed liquor high in nitrates go back to the anoxic zone, where it denitrifies and then goes back into the oxic zone. And it was operating decently well. After this, they've kind of created an anaerobic zone here on the left, and then are removing nitrate on the right through control of DO, and they've closed this recycle gate. And we'll go into much more in depth of Great Bend, but it's kind of an example to show you what is on the range of possibilities. And this might be about the best case scenario that nutrient optimization can do. So their environments, afterwards, they have anaerobic zone here on the left, where you see PO4 release, PAO growth, and VFA production. And then you have ammonia conversion and denitrification here on the right, with luxury phosphorus uptake on the right as well. Another highlight here is the city of Colby. They have a newer traditional activated sludge, probably mid-2000s, and they're facing permit limits for total phosphorus, I believe. So this plant was not designed to remove phosphorus. We think we're getting there with some of the changes. So it was basically basic activated sludge. Influent RAS came in on one side in an aerobic environment, came back through into the final clarifier. They did have some DO control to primarily save energy, but they were also seeing some denitrification occur with air control. The city of Colby has basically created an anaerobic zone up front by turning off an air header to the diffusers somewhere in this area. And then they are cycling aerobic and anoxic later on in the plant to remove nitrates, again, getting low RAS nitrate concentration to protect that anaerobic zone. So here's kind of their environment now. They have the signs of anaerobic zones early on: PO4 release, PAO growth, and VFA production. Ammonia is being converted to nitrates, and then also denitrification is occurring in the aerobic and cycled anoxic areas, and they're also seeing luxury phosphorus uptake occur. Now, they're not looking quite as peachy as Great Bend is on their numbers. But you see with the optimization, their rolling 12-month average is coming down. And if they can keep numbers like this, they should be able to meet it as long as they can not have too high of high points with their total phosphorus levels. They've also seen improvements in total nitrogen, which is an indicator that their nitrates have come down. And that again is very key to success. Also talked a little bit about fine tuning a BNR plant. And I've been to many relatively new facilities that aren't quite performing as they'd hoped. The city of Horton has a new aeromod facility, and this is actually under construction photo. They have an anaerobic zones, these two basins here, and then the flow kind of splits out around. These are clarifiers to the right and left of the anaerobic zone. They had kind of mediocre phosphorus removal given the plant design. So I visited the facility, left an ORP meter, and we'll talk about that more. And we monitored the ORP, and it wasn't in the range that you need. So they reduced their mixing from the mixer being on 24/7, so every minute of the day, and to cycling it on 1 hour, 1 hour off. And it seems to be working. Where their new plant was online, they were getting 3s, 4s for total phosphorus levels, and now they're getting into below 1 to under 2. So with this level, if they're consistent with this, they should be able to meet their phosphorus limits once it becomes into effect. But they will need continuous monitoring of that, and they're working on getting an online ORP meter to help with that continuous monitoring. So some takeaways from today, and there will be more with the upcoming webinars. First, I would really like to stress, let me see here, turn that off. So if you're just getting into this, really work on developing a total nitrogen removal strategy first. If you try going with total phosphorus and you have high nitrates being flowing around in your plant, you're unlikely to be successful with that strategy. Once you get a return activated sludge that's low in nitrates, then you can look at executing total phosphorus removal biologically. And then every facility is going to vary, but work on developing a reasonable monitoring plan for nutrient levels within your plant and for compliance purposes as well. So, many of you have probably got into the industry where you would check your settleability and your ammonia on a regular basis. With nutrient optimization, you're going to need to add a couple additional parameters to that. Most likely going to be looking at orthophosphate at a couple of places in your facility, and possibly also looking at nitrates at some places in your facility. Each facility, again, is going to be quite different there. So before we end, let's see if I can get this. I don't know why I can't get the laser pointer off now, so I apologize. I want to leave you with some idea to bounce around in your head. Grant and I have been talking with KDHE about some small group developments. So we're considering regular small group meetings, and Grant, if you want to hop in and help detail this idea, feel free. So the small groups would be by plant type. So for example, SBRs, oxidation ditches, aeromod facilities, etc., would form the small group. So you're working with plants that are very, very similar to yours, if not identical in a couple cases. Both Grant and I, and also KDHE, believe that these small groups could be really useful for both nutrient removal efforts and also just plant management, especially with supply chain issues. If you're operating the same branded, the same brand of RAS pumps, that's going to be valuable when you have issues with that. We're going to leave this with you to digest for a week, and then we'll do some polling to see interests there. Grant, do you have anything else on that?
Well, yeah, I'd like to follow up and echo that. I got to tell you, Nick, not only was it a great presentation that you just did, the attendance was fantastic. We had 75 people listening in. So wouldn't it be fun to be able to develop a cohort of folks operating plants somewhat like yours, and we can facilitate that and try to get that started and back out whenever the time is right. But I've really been looking forward to setting something like that up for a long time. I'd like to say one more thing while I got the floor here. That fellow at the beginning, Tom Stiles, who was talking, you know, he's the top dog at KDHE. He's the guy with the big stick and the big wallet that runs the water division. And it was really nice to hear his presentation. And you know, Nick and I have enjoyed the support from Tom, and then from Ryan Eldridge, who Ryan's participating today in the webinar as well in the background. So yeah, we'll bring this up again next week and gauge the interest. And there's a couple of questions that have come in, Nick, that I want to pass along to you. One is somebody's interested in getting copies of the presentations. I don't know if you can make it available as an Adobe or something like that. And then I think a refresher reminder of kind of what the rest of the schedule for this webinar series is would be helpful. So I'll kick that back to you.
Okay. Yeah, probably the best way is to email me, and I can send you a PDF or a PowerPoint, whichever one you would like. And my email should be in the last slide here. And somebody asked on recouping. Okay, so the webinar series is this. I have to click there. Okay. Okay, so yeah, the case studies are coming next week. So if Colby or Great Bend, facilities like those who are, you know, successfully optimizing nitrogen removal concepts. So this is going to be more of the science behind how nitrogen removal works, then the phosphorus removal, likewise the science and the biology there. And then we're just gonna, you know, the final week will stress again, you know, rehash, review what we've covered, so that, you know, hearing it very likely you will hear some of this information, you know, 2, 3, 4 times, and that's on purpose, to really help you understand that denitrification occurs where you have carbon and anoxic conditions, and you'll hear that more than once, and that is totally in line with what we're trying to do here. Let me go to
the presentations that are following are all the same day, the same time.
Yes. And you should have been able to sign up for all of them at once. I believe the sign up link, if you only sign up for like today, you should be able to go back to it and click on the remainder of the weeks to do that. Okay. So I wanted to highlight and the KDHE sponsored technical assistance. Grant and I don't do this for free. So this has been paid for by KDHE. Now, their on-site technical assistance to all municipal plants in Kansas. I have the ability to provide on-site assistance to you. I also have the ability to provide some loaner equipment. So I have a photometer and some reagents that can test for ammonia, nitrates, and orthophosphate that I can loan you. One facility's had one for almost a year. So if you're diligently working with it, I'll try to work with you. They're trying to get their own, but you know, budgets and everything else. So I'll also help walk through your plan to figure out where the right environments can be at the right times with the right conditions. We also have Grant that can help remotely. I can work with him. We can all get on a conference call. We can also bring him up when I'm on site, hopefully. So all of this is available at no cost to you. So if there's any questions, reach out to me. Reach out to Grant directly if you've worked with him in the past. And again, I do have some availability of loaner equipment at this time. Just about to loan some out. But I also have a little bit of budget to add more every year. With that, feel free to contact me. Here's my information. I'm going to stay on the line for a few minutes after this. So if there are any questions, feel free to turn on your camera and your microphone and get back to me. So with that, feel free to hop off. Hopefully we'll see you next week or one of the subsequent ones.